Yeah, fair. That's the first thing on the video. I knew it. All right, so on the notes. They want us to find the equilibrium solutions. It's been a minute since we had talked anything about equilibrium solutions, like the very first day of this unit. Does anyone remember what an equilibrium solution is? Yeah, when what equals 0? Yeah, the derivative. So it's when your slope equals 0, it's where your horizontal asymptotes are, it's where your derivative equals 0, that sort of thing. It's your equilibrium solution because the rate of change is not increasing or decreasing, it's staying the same. So it's your equilibrium. All right, so we want to find the equilibrium solution. So that's going to be where dp dt equals 0. So they're talking about a population of minks. I only know what minks are. I know that they're furry because back in the day they used to have mink jackets. But I don't know. A sexy fox. Interesting. All right, so a mink is a sexy fox. And their population develops according to this, where T is in years and P is in thousands of minks. Cool. All right, so find the equilibrium solutions. We're going to say 0 equals negative P to the third plus 7P squared minus 10P. We can factor, and I would factor more than a P, a negative P. All the maturity is coming out right now. So now we're factoring. We're multiplying to positive 10, but adding to negative 7. Negative 5. Negative 2. Okay. So what are the equilibrium solutions? 0, 5, and 2. Or if we are thinking about the units for the problem, 0 minks, 5,000 minks, 2,000 minks. Okay. So what does this mean? We're going to say the population does not change if we have 0, 2,000, or 5,000 minks. And by mink, I mean sexy foxes.
Can we have a kill a sexy fox?
No. No, thank you.
I feel like that would be a question that we can ask.
Today, while the tours were happening today, the first time the tour came by, I was playing Dr. Dre's song because we were listening to Backyard Barbecue or whatever that station was. And then the second time the tour came by, I had just done an evil laugh where I was like, "Mah!" like shaking my head. And that's great. So lots of, but this wasn't kids, this was parents. So that's good. That's good. All right. So sketch the slope field for this differential equation. You don't have to put a lot of detail. Just be sure to include the equilibrium solutions and some values in between them. So we're going to go ahead and draw like a little slope field. And I'm just going to say like 0, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000 so that we can do like, everything a little bit above and below. I'm not including below 0 because I don't think we're going to have negative 1,000 minks. Not positive, but I'm pretty sure it's not going to happen. So there's 2, there's 5, equilibrium solution right there, equilibrium solution right there, equilibrium solution right here. Okay. So if I look back, if I plug in 1 here for 1,000, I get negative 1, times negative 4 times negative 1. Negative. Okay. It might be interesting with the 3 and the 4 to figure out which one's steeper, you know, because they're probably not the same. Okay, so if we do negative 3 times negative 2 times 1. Positive. That's a positive 6, right? Am I doing this in my head? Am I all by myself? Was that a positive 6? Negative 3 times negative 2. Yes. Okay. If we plug in a 4, we get negative 4 times negative 1 times 2. Also positive, but more steep. Right? More steep. Okay. And then what happens if we plug in 6? Negative 6, 1, so. Yeah. So that's approximately what our slope field would look like. My first degree, my instance is like, Miss Rose, can I close that door? And I said, sure. And he was sitting right here, and he opened it, like, hit the door, so it slammed. And the clock fell face down, and the glass shattered. And I was like, this was yesterday. So I told him he owed me a new clock, but you can't even tell that the clock is broken. Like, the whole frame is gone. I threw that away yesterday. The glass is gone. So it has no face, like nothing covering. But I think it's easier to read now because there's no glare. So kind of worked out. Thank you. Thank you for breaking my clock. Yeah. I'm not telling you. All right. So there's our slope field. What happens to the populations for values of p sub 0 between the equilibrium values? So if we started with a population of 3,000 minks, and we started tracing that solution curve, what would happen over time?
It decreases.
Wait, 3,000?
That increases.
It increases. 3,000 would just straight up increase.
Yeah.
Yeah, if we're starting with 3,000. Yeah, so it would increase to 5,000 and then it would level off, right? Okay. What if we started at 1,000? It would decrease and then flatten at 0. Well, what if we started at 10,000? I'm assuming it would decrease until it hits 5,000. Okay, so yeah, so if we start at 0, it would increase. Sorry, if we start at 3,000, it would increase to 5,000. Are you guys okay with me writing K? If you start off with 1,000, it would decrease to 0. I wrote the K because I didn't have enough space for 3 zeros. But I was like, aha, that's a clever way to make up for my mistake. All right, and then we said if we started at 10, then it would decrease to 5,000. What if we started at like 1,575? Go down to 0. Okay.
What if we started at 2,000?
Stay at 2,000. Yeah.
Sounds like my investment strategy.
Yeah. So we said what happens to p-values larger than the largest equilibrium value? We already answered that. It just goes down to 5,000. Okay. Why do you think the mink population behaves the way it does? There's not necessarily a right or wrong reason for each of these, but what are you guys thinking?
Well, there's a maximum value that can hold.
Okay.
So if they're up anywhere in that threshold, they're never going to be able to cross it. But you also need enough population where if some disaster would befall you, or like there was a virus, like none of you would be able to survive to continue breeding. If you
Right.
lower the population, you're not going to have enough to breed
Yeah.
at an exponential rate, and you're also, so you're just going to slowly lose.
Right. Well, it's like the predator-prey idea, right? So if you have too many minks, then everybody is like the same type of predator. There's not enough prey to go around. There's not enough food to go around, so the population is going to decrease until it kind of levels out, where it's a little bit more balanced. Or if we talk about this, like this is down here where you are thinking about mink are prey to what? People trying to make coats is what they're prey to. And there's too many people making coats, not enough minks to go around. You know what I'm saying? You guys didn't even bat an eye. You were like, yeah, obviously people. People are the one thing that minks have to watch out for. And foxes are mad that minks are sexier, and so they have to watch out for the people and the foxes. It's terrible. Yeah. That's so sad. Anyway, so yeah, there's a lot of things that kind of go into this, but if you look at data of populations, it always follows a logistic curve. So in every population, there's always a carrying capacity, always. You could actually start graphing the data of the population of the world, and you can see that we're already hitting the top of the logistic curve where we're starting to level off, which is kind of interesting. Oh, I'm not sure. I'm not sure, but I know that we are already leveling off because I studied it in one of my math classes. So that's how I know. Right. Well, if you look at the data of the logistic function, we are approaching our asymptote. I don't know how quickly, but it's happening. All right. So those are the notes. Those are the notes. Those are the notes. Let's go ahead and get started on the practice problems.